All right. Go ahead and get started. I hope everybody had a good fall break. Hope you got better sleep than I did. So today we're going to continue along the journey of looking at organic chemistry in a pretty simple algebraic way. And so I'll give you a lot of examples of that today. And again, this might look scary for people who don't like chemistry, which seems to be most engineers, except for chemical engineers who love chemistry. But anyway, the fact of it is it's just a relatively simple algebraic operation. That's the way I want you to think about this. So don't look at it as whatever negative experiences you've had with chemistry in the past. This should not be it. All right, so it's just a matter of knowing how things fit together and what in some cases is spat out when they do fit together. All right, so I encourage you that when you go home after I'm done, so when is the test? Wednesday, all right.
Is this on it?
No. What is the last lecture? Was it today's? No. Was it last Friday's? No. What's that? You didn't have class last Friday. Was it Wednesday's? No. It was Monday, right? That should be the last lecture that's on this upcoming test. So more than a week ahead of that time. All right. The 2018 and 2019 exam keys should be on the website. I'm going to get the 2020 up there sometime before midnight. Also the office hours. I assume you'd like them moved to Tuesday rather than Thursday. Okay, so I can move them to Tuesday. I'll send out an email when I get back to my office so that everybody knows.
Why is that? I mean,
it's before the test rather than after the test.
That is also very true.
Okay. All right. Anything else while I'm on the subject of the test? All right, so we're good to go, right? All right, everyone jump out of your chairs in excitement over the test, I'm sure. All right, and so all the examples of what I'm talking about today are step growth polymerization. Yeah, question.
Sorry, just to clarify, the exam, it's not uncumulative, it does have some parts from test 1 in it?
It's not going to have the detailed stuff from test 1, so you're not going to see equations from that first part of the class. But, I mean, free volume, I can't stop talking about it.
Will the first question be like a big 6?
It's going to be a big 6 question, yep. Yeah. But, I mean, so the detailed stuff, no. But, I mean, there's just common concepts that we can't do without. So, I hope that makes sense.
Yeah.
Okay. Anything else? Yes.
Will you ask us any specific details about the video that we haven't really gone into during the rest of the material at all?
I may ask something about the video that I didn't talk about in class. Although I think I talked about almost every segment of that video, just in passing at least. So again, for the gotta be the 6th time, watch the whole video, okay?
I'm saying you're not going to ask a question like, who produced the video?
Oh, no, God, no.
Yeah.
Yes. What was the English accent being used? No, I'm not going to ask you which one. Manchester versus something else. All right. Any other questions? All right. So yeah, I mean, again, that video should be able to, look at it and understand why different things cause different behaviors in the crazing process. All right. So getting back to today's lecture, step growth polymerization. Which is what we've been talking about all along, ever since we started talking about ethylene gas. It's a form of step growth polymerization, so you're just stepping things together. And as you'll see, and as we'll talk more about later on, in the context of step growth, ultimately you're stepping two things that are very large together to get to the high molecular weights that we need to get to form something that we consider a polymer that's a high enough molecular weight to be considered a plastic. And so part of the struggle is making sure that the chemistry and the conditions are pure enough so that we can get to these high molecular weights. And there are a lot of things that can go wrong. Things that chemical engineers typically worry about, but you guys at least need to know what they are and why these are important barriers. And so, Step code polymerization includes both condensation and addition. We've been talking about addition all along here when we talk about ethylene gas and everything else in the Big Six so far. Condensation is not all that different. The only change is that there's a side product. And as you'll see today, those side products are either simple things like water, we see a lot of water, hydrochloric acid, and then there's various alcohols that can come out of some of these things, but relatively small molecules that aren't the plastic that we want. Now with ethylene gas, all we get is polyethylene, and that's a pure addition reaction with no side products. All right, so that's nice to have. Condensation products, it's not as nice as addition polymerization, but it's not the end of the world. They have vacuums and things like that pull out these side products, and the reaction proceeds merrily along. And as you might imagine, for PET especially, you got to pull that stuff out, or else the reaction goes backwards. All right, so this is why we, when making these materials, they remove these side products relatively quickly. And so that gives us that side molecule, that small molecule, and this is an example that I want to start with, and ultimately you'll need to be familiar with what I'm showing you here, which is this CH3N2, and then we have the COOH, and this is, we talked about it before, carboxylic acid, and I show it as a shorthand here, but in reality you should already know that this is carbon double bond to an O followed by the rest of the molecule, right? Should be at least passingly familiar with this. We talked about this when we talked about coupling agents. I showed you an example of this. And so what we're doing is we are engaging in these condensation reactions. We are engaging different components with different pieces of the other molecule. So these guys get together and they spit out water, and at the same time they create this completed bond, which again still has the carbonyl in it. All right, but now it's part of a larger molecule. Okay? So make sure after the test, when you have the presence of mind to think about something else besides what you were studying for the test on Wednesday, go back to this lecture and make sure that you are able to, in your mind's eye, translate what you see on this page into the three-dimensional structure. Very important that you get comfortable with that. Addition polymerization, which again you guys are already familiar with, but here we're talking about a different context. Coupling reaction without loss of any small molecules. We're not making water, we're not making HCl, we're not making any other molecules or alcohols. And this is showing something that's new, the isocyanate structure reacting again with, what is this molecule, organic chemistry, refugees? Come on, I know there's 3 or 4 of you. Ethanol, all right. We're all very familiar with ethanol. Well, at least some of us are.
I try to block OChem out of my mind.
Okay. Well, this is a very painless part of OChem. So ethanol is the reactant here, and it reacts with the isocyanate, and you end up again with C double bonded to O, and in this case oxygen is the ether in the chain. And so that's our classic urethane, and we already talked about polyurethanes, and so you know if you grow these long enough, we can make very useful biomedical polymers out of them. All right? So again, when you have a chance, get very familiar with these shorthands that I'm using here. So in step growth polymerization, monomers with 2 reactive groups, bifunctional monomers are essential. This is the simplest version of this. If we are reacting A and B together, we would get D. And then if we have a reaction that involves AA rather than just A and B together, we get AD. And if we want to, we can add B to that, or perhaps add A to it, and then we get more of the same molecule, but in a polymeric form, or at least a oligomeric form, short chain form. And so we can do the same thing. We come with A plus BB together and get a D and a B together and add in an A in this context and get to DD. All right, so it should seem simple. And the idea, of course, long term, is to make this number of Ds very, very large, in the thousands, as you should now know. Any questions about that so far? All right, so this is maybe needlessly algebraic, I don't know. If you have A and B together, their union in the middle gives you rise to D, and then you can add in A's on the end to give you another unit of D, and then add in B's on the end to give you another unit of D as well, and just keep going until eventually it grows to be a polymer. All right, seems simple on paper. Reality of it is, as you'll find out, is not quite so easy. And again, we can have other versions of AB and AB to give us that D complex in between them, and then start adding things on the end to eventually grow it to being a polymer. So you can see there's a lot of ways of getting to where we need to go. Okay, so let's think about this now. So, which of the following monomer or monomer pairs can undergo step growth polymerization? And so the key here is that we need to grow, and we need to grow in 2 dimensions, or 2 directions at least. Let's call it that way. You need to continuously grow, and as you'll see, continuously grow typically very quickly. All right, so this first example, A, will that give us a polymer in the end? I see one no. Yes?
I would say no, because there's nothing, you're not adding it to anything.
You're adding it to itself.
You're adding it to itself, okay.
Okay. I mean, yes, I should have qualified that. So you're adding it to itself to make a polymer of that particular molecule. All right. And again, this is a carbonyl. So that's what it says OC here. That's a C double bonded oxygen. And we have the OH. And this guy can react with the OH on the different chain and start spitting out water. Yes? This question? Okay. So we know then that we have a functional group on the left-hand side and a functional group on the right-hand side. And we know, as we saw on one of the previous slides, that those can react together and spit out water in a condensation reaction. And we know that this process keeps going and going because each end is reactive. So it can keep going on and on, theoretically, to infinity. There's lots of practical barriers to infinity, but it can go to very, very large lengths. Okay?
So the first one's a yes?
First one's a yes. All right, so this one can work. Well, I guess I should use green. All right, green means go. What about B?
That looks a little tougher.
Why is it tougher?
It has the reactive groups on the molecule on the left, but on the molecule on the right, it has a very unreactive group that what we're adding it to, because what do you call the CH3?
Yeah, CH3. So it's
methyl.
Methyl. Yep.
Methyl. That does not want to change. It's a carbon.
Right.
Bonds. They don't like to change.
Yeah. So those are direct carbon-carbon bonds, and as I keep beating you guys up about, it's a very strong bond. It doesn't want to react. It's actually very hard to get carbon-carbon bonds to react. It can be done, but it's not easy at all. And so what's going to happen is you may have this able to react with either one of those 2 ends, but as was pointed out, this CH3 is very stable and it's not going to react with anything. So what could go on here, you could have this guy could come over here and react with that end, and then something very much like it can show up and react with that end. All right, and so now we've added 2 of these to that, but what we've also done is we've ended it with 2 of those. All right, and so we have a situation in which we've grown it, but then we can't grow it anymore because the CH3s are basically poisoning the reaction. Does everyone see that? Okay, so again, it's once you learn the rules and learn what all these symbols mean, it's pretty straightforward. So the answer here is a big no. That's not going to go anywhere. You get a little bit of growth, but we don't want a little bit of growth. We want thousands of additions. We want thousands of reactions, if not tens of thousands of reactions. What about C then, knowing what you know?
Yes.
All right, yes. So C has reactor groups on both ends of everything. So that'll keep going. And so if we have this left-hand molecule present in equally stoichiometric amounts to the right-hand molecule, they'll just keep reacting theoretically to infinity. Nothing is stopping them for linear growth. Does everyone see that? All right, now what about part D? No. So part D has a limiting end. And so that is not going to participate in chain growth. And so again, you can get some reactivity, but then you've poisoned it, you've stopped it, you've eliminated an active group. And so we call these bifunctional monomers because they have functions on both ends. But this is not a bifunctional monomer, it's only a unifunctional monomer, if you want to get into the details of it. Yes?
So what would happen if in C you replace CH2 with CH3?
Which CH2?
This one and even this one. Like since they're in the middle, they're not on the end.
Yeah. Oh wait. You want to put a CH3 in there, but that's going to terminate. You can't have 5 bonds per carbon.
I don't really understand.
Well, I mean, it's a good question, except that you have to be able to make it happen. So,
Okay, let's say
what's
it happen.
well, what's in the middle here almost doesn't matter.
Okay.
All right, this is just algebra. You could put, and people do this. You instead of 2 CH2s, you could put 5 CH2s in there. The reaction should still theoretically keep going because what's in the middle is just being carried along.
It's kind of just about the end.
It's all about the ends, yeah, right. And that's what we just talked about is commonly done because maybe you want something special in there besides CH2s, and that's perfectly fine as long as it doesn't interfere with the reactivity of what's on the end. Yes?
So can you explain how the end on D is going to cut it off? It's going to like limit the growth of it?
Yeah, so in D you've got the CH3s, and the CH3 is not a functional group. It's not going to react with anything. You're asking it to, in order for it to react, you're asking it to break that carbon-carbon bond, which it does not want to do. All right, carbon-oxygen bonds obviously can be broken. That's what we're talking about here. Those can be broken, used to spit out water, and the reaction can keep going.
So if you see that as any end group, you're just going to call it a no?
If I see, yeah, if you see that as an end group and you're being asked whether or not this will keep going, then the answer is no.
Okay.
Yes?
People add the unifunctional end group compounds to like limit the chain size.
You can if you want to, yeah. Typically you don't want to, but if you're making something very short, then maybe you would use that. You might have, so you could have 10 of what's on the right-hand side and 1 of what's on the left-hand side, and eventually it's going to shut down the reaction. Okay, so if you want to make something relatively short, then yeah, that would work. Any other questions? Yes?
Does CH2 work on the end, or does that never happen?
You can't have a CH2. You need to have 4 bonds per carbon. I guess if that's one rule you guys aren't aware of yet. Every carbon has 4 bonds.
Yeah.
All right? So CH2 would only be 3 bonds if it was on the end. Any other questions? All right, so these reactions proceed through a formation of dimers, which is 2, trimers, which is 3, tetramers, which is 4, quadramers, which is 5, by reactions that are identical in rate and mechanism. So we can have, as we've been talking about so far, monomers plus monomers giving us dimers, but you can also have a dimer, and as long as it has those reactive groups on both ends, it can react with a monomer to give you trimer, and so forth and so on. As long as those reactive groups are present on the ends of these things, it doesn't matter how long they are, theoretically they can react and make pentamers is the word I was looking for, 5-unit polymers in the end. And ultimately, especially when we talk about really high molecular weight species, we have some type of N-mer and M-mer, and these can be very large numbers, and those guys add together to give you your 1 million unit chain, for example, in the case of polyethylene. All right, and theoretically that can happen. Now, practically speaking, hopefully you're realizing that, well, they got to find each other. You have a 500,000 unit chain, and there's a little N group on it, and it's looking for the other 500,000 unit with the reactive group on it. They got to find each other. So kinetics starts to rear its ugly head in this context. But everything we're talking about is an individual step. Any questions about that? Okay. All right, and so we get into a little bit of the math here, which isn't too bad. How do we know what the molecular weight of the polymer is? And so Carruthers, among his many other achievements, used a pencil and paper to come up with a series of equations which are still in use today. And so the Carruthers equation is the relationship between the number of repeating units, not unites, units, defined as x sub n, and the extent of reaction, which is p, for step growth polymerization. If we consider the polymerization of some type of monomer AB, like we've been talking about so far, assuming a starting number of molecules referred to as n sub naught at time 0, and then referred to as n at some time t, then the extent of reaction at time t is defined as this initial number of molecules minus what is present divided by, again, the initial number of molecules. And so that gives you this extent number. Okay? And then, since x sub n is given by this ratio of the starting number of molecules divided by the number of molecules n at some time t, then we have the Carruthers equation, which is written as x sub n is equal to 1 divided by the quantity 1 minus p. And so what we'd like to see happen, and I guess the next equation kind of helps illustrate that, if m sub n is equal to the molecular weight of a monomer times x sub n, and we know we want the polymer to be ginormous, we want it to be huge, then of course what we want to see happen is make p very large so that this ratio of m sub naught over the quantity 1 minus p also becomes large. Okay? And so we want to make that number in the denominators as little as possible. And so that's kind of the game that we play in this context when we think about this. Yes?
So is P a percentage then? Or is it
P is a fraction, yeah.
Gotcha.
You'll see it. I have another slide here that shows that. Any other questions real quick here? All right, and so if we're polymerizing this particular molecule, and so this is just a monomer, we don't have to have two different monomers that are radically different from each other to react and form a polymer. This will form a polymer just fine. And in this context, whoops, I didn't want to do that. If P is only 0.9, which isn't bad, we get an x sub n of only 10. And if we have a certain m sub naught associated with that particular starting unit, then we end up with a number average molecular weight of only 1,310 grams per mole. All right, so it's not a liquid anymore. It's not really a plastic though. 0.95, we go to 50. Now we're at 6550. It's getting in a reasonable polymer size. That could be could still be a flaky solid, not so much a very good plastic. So hard to say exactly what the form of that would be. Although with all the secondary bonding, it's probably a flaky solid or maybe a powder in bulk form. We go to 0.99. Now we're making that number in the denominator relatively small, and it gives us a relatively large fraction. X sub n is 100. Now we're at something that I would say that's a polymer. All right, that's 1,300. And we work in the lab with polycaprolactone that's 10,000 grams per mole. So I know that's a polymer. And then where we really drive things is when P is as large as we can possibly make it. X sub n is 1,000, and now we're at 131,000 grams per mole molecular weight. So that's a respectable plastic for sure. Okay? Any other questions about that? Being at 1,000, what we have like. All right, so we can do the same thing. We talk about the polymerization of AA and BB. If the initial number of AA and BB is the same Carruthers equation applies. All right, so we're still trying to get X sub n to be a very large number, even if we're talking about things that are not the same monomer, which we talked about a lot. If there's a special case, and again, Carruthers worked this out with a paper and pencil. If AA is not equal to BB, then we think about this ratio R of the number of AA molecules versus the number of BB molecules. He came up with this equation where this X sub n is equal to 1 plus R, again R being that ratio, divided by the quantity 1 plus R minus 2RP. And so if we think about a situation where we have 5% more B than we do A, and we're asking this thing to go to 0.999, then we're still stuck with a X sub n is only 39. All right, so that's telling you that these systems, and this is where the reality of polymerization reaches likely head. Small changes in the ratio can lead to big decreases in efficiency. And so we've made a substantial change. And so we're only at 39. All right, so we're not going to get a very good polymer with this system if the stoichiometry is even just a little bit off. Okay. That's 1,000 when things are the same, when that ratio is equal to 1 instead of 1 over 105. And so we can represent this graphically, where we have x sub n versus extent of reaction. And so you can see that it's actually pretty crappy values until we get to 0.99 or greater, and then it starts to go up to values that we can consider will give us an actual polymer at the end of the day. All right, so this is to do with basically this poisoning of the reaction by things not giving us what we want, actually. And then we think about the variation in x sub n with the stoichiometric ratio. Again, in this case, we have these very small changes, and we're looking at when it's 1.0, we can get to x sub n's that are very high, but if it's 0.998, then the x sub n is more limited. All right, and so you can see that we'd like to have something that goes to the largest value possible, but if that ratio is not dead on 1.0, then we start to limit ourselves in terms of the x sub n's we can reach. Okay. So what's needed for, I should say, successful step growth polymerization is extremely pure monomers. We don't want anything else in our system. And this is where what chemical engineers do becomes very important. You've probably seen these gigantic stainless steel reactors that are shiny and they're sitting in clean rooms and everyone's wearing a bunny suit. All right, all these things are necessary steps in order to achieve success. Very pure monomers, very clean conditions, everything's very well controlled, temperature is minutely controlled to 1/10 of a degree, everything's perfect. And if that's the case, then we have no unwanted reactions. We get very high values of P, meaning that x sub n is large, meaning that the molecular weight is in the range of useful plastic, and a precise balance of functional groups, which within reason isn't all that difficult, but it just shows you that that's a very important step. What can go wrong, and we talked about some things involving impurities, where something in that monomer is not what we thought it was going to be. And so we've talked about some of the side effects of that already, where we have unfilled groups, we have branches, we have kind of vacancies in the polymer chain, if you want to call it that. And all those can cause problems in the context of reaching these high molecular weights because they drive it off in a different direction. And so very small impurities can cause big problems and unwanted side reactions. Physical loss of the monomer during the reaction usually isn't an issue, but it can happen. And these are gases in many cases. We're talking about ethylene gas. All right, we start making a solid. We want to make sure we don't lose the ethylene gas, or more likely, ethylene plus some other monomer that's also a gas. We have to make sure that the stoichiometry is preserved so we don't get to an imbalance that can dramatically decrease our values of x sub n and dramatically decrease the molecular weight. Any questions about that? All right. So then we get into some of the other details. So this is, again, it's all plug and chug. It's just algebra. It looks like scary chemistry, but it shouldn't be. And so if our target for D is a polyester, and you guys now know what the ester group is, right? It's that COO. In your mind's eye, you should be seeing the carbonyl and the oxygen ether in the chain. That is the ester. We're trying to make a polyester out of this. All right, polyethylene terephthalate is a polyester. So obviously, these are important materials. And so if we have A, which is carboxylic acid group, again, hopefully that structure springs to mind in your head, and we're reacting it with something that has an OH group on the end. And so this is what we talked about earlier, where the middle is something, and the ends are something else. All right, and these are the ends. And so we tailor our monomer by putting these ends on it, and whatever's in the middle ends up in the polymer chain. Okay, it's really algebraic at this point. So we put stuff that's on the end that's active, And in this case, when these two guys react together, the side group is, or the side product is what? Water. Everyone see that? Hey, you're doing organic chemistry in your head. Amazing, okay? So you get water out of this. 2 hydrogens, 1 oxygen, water. All right, we have 2 hydrogens. One of these oxygens gets chewed up and is used to make water. If we instead react, let me go to that. If we instead react this guy with that guy, what do we make? Hydrochloric acid. Does everyone see that? Chlorine comes off, reacts with hydrogen, gives you HCl. Any questions about that? All right, and if we then also turn around and react this guy with that guy, what are we going to make? Organic chemistry people? What? HOR, which is an... Oh, come on. It's not that scary. It's an alcohol, all right? I know I saw 4 or 5 people raise their hands about having organic chemistry. Alcohol should be kind of familiar. All right, so you've forgotten it so completely that you can't identify that. So we make an alcohol, and it's not just ethanol. You have propanol or butanol or things that'll kill you, like methanol. All right, so it's not. Don't drink methanol. Ethanol is okay within moderation. Methanol is really bad for you. Anyway, but these are all alcohols, just some kind of R. And again, think of this algebraic as some sort of organic something or other with an OH on the end. That is an alcohol. Polyamides. So D now is our target still. We're making a carbon with a double bonded oxygen on it, and an N and an H. And the H is coming off that N. We talked about this last time. And the same kind of strategy applies. We start with these different N groups on our monomer, whatever's in the middle. Doesn't matter. These are the N groups. And instead of OH, we now have NH2. And we're still spitting out water. We're still spitting out hydrogen chloride. We're still spitting out an alcohol. So it is just plug and chug. Everyone see that? Again, I urge you to get comfortable with what is not written out in these structures. And then polyurethanes can be the NH, the C double bonded oxygen, and an ether in the chain, or the NH, C double bonded oxygen, in this case another NH in the chain rather than the ether oxygen in the chain. And so we can start with NCO, which is called isocyanate, and we have N groups here, and we make very similar things. We make water, and we can make alcohols as well, all right, depending on how these react. So it should be pretty straightforward once you start looking at these chemistries. Okay, so which of the following monomer or monomer pairs can produce polyamide? Can A give us a polyamide? No, why not? There's no nitrogen in it, okay? This should not be a trick question, okay? There's nothing in it that will give us the NH, which is what we call polyamides, all right? So we know that that one is a dead duck. And then the second one, B. So we do have our nitrogen now, so it's not a trick question anymore. Will this give us a polyamide? Why do you say that?
It's on the end. The B is on the end.
The NH is on the end, you mean?
Yes.
Okay, but what about what's on the other side of the NH? NH2 molecule.
Hydroxide.
Wait, what is it?
No, sorry, these. But I meant like over here.
Yeah, so there you got a CH3, right?
Which doesn't want to break.
Which doesn't want to break. Carbon-carbon bonds are not going to break. So we know that this one is also not going to give us a not going to give us a polyamide, all right? Because the CH3 issue. Everyone see that now? It will react once for sure, but then after that, this guy and that guy have gotten together and killed off this activity on this other end, and then an 11 shows up and kills off that activity. We made a molecule, a very short oligomer, but it's definitely not a polymer. All right. Again, thousands and thousands of linear reactions are necessary. So part C, okay, so we have nitrogen present. That's good. So it's capable of making a polyamide. We have bifunctional groups on both of those monomers, so we know that this one is going to give us a polymer. Hopefully everyone sees that by now. And then this last option, D, is that going to give us a polymer?
No.
No. All right. We have the CH3 on the end. We have a carbon-carbon bond on the end. It's not reactive. It doesn't matter how much of this you put into it, you're not going to get the polymer you're looking for, which should consist of those two monomers joined together. Everyone see that? Should start making sense. Again, please become familiar with what is not written out there. Okay, so some examples of things that are made by these techniques. Polyethylene terephthalate, which everyone should know how to spell by now, because I do take off for spelling. We have our monomer, AA monomer dimethyl terephthalate, which is showing you here. And so we have that group present. We have ethylene glycol. And what can happen is that this OH can come in and react with this guy and make that reaction continue. And so we end up with the polymer that we're looking for, that we all know and love. And what else do we make? No, not this case. So there's many different ways of making polyethylene terephthalate. You guys are thinking of the one where it reverses, and water is very important there. This is not that reaction. This is a different reaction. There's like 8 different ways of making PET. All right, so this one's going to give you CH3OH, that alcohol monomer. All right, so the one we don't want to drink. Yes?
So there's CH3 on the ends on this one.
Yeah, and that has to go someplace.
Okay.
All right, so I guess maybe I need to spell this out. This is maybe not clear enough. What's in here is CH2. That's where the CH2 comes from. Okay. And yeah, this may be a shorthand you're not familiar with. So this is CH. All right, so hopefully that helps. So now you know where the CH2 comes from. That's part of our final structure. All right, we have a CH3 here, and you can see that this carbonyl group, that guy there, and this guy there is preserved in the end, and we're adding this CH2 from the ethylene glycol to it. This CH3 has to go somewhere, and so it finds one of the OHs and makes methanol. The stuff you do not want to drink. Eat some alcohol, but you definitely don't want to drink it. It's a great way to go blind, kill yourself, all kinds of nasty things can happen with that. All right, hopefully that's a little clearer now. Again, it's algebra. It's not exactly the same as what you've seen before. You might want to take a look at that other reaction. You'll see that they are different from each other. We get a Young's modulus of up to 3.1 gigapascals. This is a very pure PET when you get that level. Tensile strength 75 MPa, elongation up to 150%. TG, now of course this is pure. All right, we know that we don't have pure PET. Nothing is pure, pretty much. And the melting point is 260, which we're sort of familiar with for polyethylene terephthalate. Very lightweight, good gas barrier, and a fair barrier to water diffusion, which is certainly important to us when we're talking about drink bottles. Impact resistant, naturally colorless, good transparencies. Can also be used, especially if it's recycled out of the 2-liter pop bottles, as fibers for textile applications. Polycarbonate. Now, I talked about this last time. This is the polymer structure that you will need to memorize. Think of this as structure number 7. Okay. Do you have to know it for this test on Wednesday? No. Okay. No, you do not. Everyone clear on that? Don't freak out and try to memorize this in 2 days. It's not that hard, but don't worry about it. So in this context, we have as our monomer what's called bisphenol A, which I think I mentioned to you previously, the dental composites that are nice and white and go into your teeth and replace whatever nasty cavity is there. That's made from TEG-DMA and bisphenol A. Bisphenol A is a huge concern when we talk about plastic containers, especially being used to feed babies that might have bisphenol A in it. It can still leach out and do unfortunate things to infants. And we're also combining that in this context with phosgene. What has phosgene been used for, most infamously? Come on, no military types in here might remember the nasty history of...
I remember an article of this once, but it was years ago. I can't remember what it was used for.
Phosgene gas was used in World War I. It reacts with the tissues of your lung and makes hydrochloric acid. All right, so you basically...
literally turns someone's lungs into kind of distilleries where you will...
I don't know about distilleries. Making hydrochloric acid is not a distillery, but
it makes acid in your lungs.
It makes
that
acid.
Literally fills them up and melts you from the inside. Not very.
I don't know about that, but I mean, it does. It makes your lungs not work. So you just basically gasp yourself to death because your lungs aren't working. So, not a very good thing. So, fortunately, that's been outlawed. So we don't use phosgene gas anymore.
Does it have any other use besides a chemical weapon?
It's used here. You can make polycarbonate out of it. All right. So it does. It's actually a very useful industrial chemical. Okay. It's a great way of reacting to make different types of polymers. And this is one example. So we're making bisphenol A carbonate or polycarbonate. It's like chlorine gas. Chlorine gas, no one should have anything to do with chlorine gas, but the industry uses it all the time. Like when those rail cars periodically come off the tracks.
Does it need to be in gas form to bind with
This?
the other?
Phosgene? Yeah. It works best as a phosgene gas. Relatively homogeneous, again, pure form. In the case of polycarbonate, this is one of the examples of polymers that are typically pretty pure because we need it to have good modulus, good strength, good compressive strength, elongation to break of up 150, melting temperature is 267, glass transition temperature 150, and its applications are high impact resistance materials or plastics such as the glasses that many of us are wearing. And the optical properties of polycarbonate are one of the things that make it very popular for that application. It's very clear and doesn't really haze very easily. So polycarbonate is what we call an engineering polymer. All right, the big six, those really aren't engineering polymers, but polycarbonate is an engineering polymer. You can build stuff out of it, and it should stay the same shape when load is applied, all right, within reason. Nylon 6,6, which I mentioned last time very quickly. We have adipic acid reacting with hexamethylene diamine, something we use in the lab a lot. And we have, and again, this is a shorthand. So all those little things between the parentheses, those are CH2s. CH2, 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 CH2. All right? And so these end groups react with each other, and you end up making what's called nylon 6,6. So again, those 6 carbons within each of the monomers have now been incorporated into the polymer. And that's why we call it nylon 6,6. Very useful material. It has, as we talked about before, strong hydrogen bonding interactions between the different polar groups on the chains where hydrogen gets involved. And these examples that are shown here involve the hydrogen on the nitrogen. Other hydrogens can also react with these oxygens, but this is just being called out because they match up very nicely. Pretty high melting point, resistant to heat, strong and stiff, tensile strength greater than 90 megapascals, pretty good strain. Modulus is high. It can be made as a dense structure with small pores. It can be difficult to dye because of that. Applications, carpet fiber, some airbags a lot. Tires, when you see fiber reinforced tires, we're talking about nylon fiber that's reinforcing them. Okay, so that's where most of it goes. Belts and hoses as well also involve rubber and nylon fiber mixed together. All right, and that's what gives us hoses that we can typically rely on for most applications. Polyurethane. All right, so polyurethane. Yeah, we need a rule here. RNCO. We're talking about reacting with an alcohol. Gives us these forms. The isocyanate group reacts with the hydroxy group to form the urethane group. Again, now we're using R's here as kind of our shorthand. And so the isocyanate group reacts with the amine group to form these polyurethane structures, and we talked about that before, but these are just some examples of what can be incorporated. So as you might imagine, all these R's can be just about anything. There's tons of polyurethanes because they've made R just about everything when it comes to polyurethanes. Reacting a monomer containing at least 2 isocyanate groups with another monomer containing at least 2 alcohol groups, and so this is one example of what can be done. react all these things together. We have our soft segment and we have our hard segment. In this case, the molecular weight is relatively low. And then we get into some more details of how polymers are really made. Polyurethane is usually synthesized by a two-step method. And what you're doing in this context is you're synthesizing a pre-polymer. So you make something that's got a certain polymeric component to it, and then you ask that to react with other monomers. And you end up making a longer structure. So you have diisocyanate or a diol, and again, R can be just about anything. We add the catalyst, we end up with whatever is in these particular pre-polymers, and then you start polymerizing everything together, and you end up with a polyurethane where hopefully these N values are large. The soft segment is the polyethylene part, and the diisocyanate with all those polar groups in it is the hard segment, which engages in hydrogen bonding. And we have examples here of diisocyanate, methylene diphenyl diisocyanate. It looks scary, but again, it's all out here on the edges. Don't worry about what's in the middle. We're just taking that scary stuff in the middle and polymerizing it using everything we've talked about before. These different reactor groups. You get a soft segment, and you can take this soft segment and make polycaprolactone diol. I talk about polycaprolactone a lot. You have 5 CH2s in polycaprolactone, and you just keep growing that structure until it's long enough to be useful. In this case, you're making something that's non-degradable. Polycaprolactone is degradable. And you have different extenders, which consist of some R in the middle. In this case, 4 Rs, or 4 CH2s, and R equals 4, and then OH active groups on the edges. And the same things here with the diamine. In this case, we also have the 4 carbons in the middle. And it's very algebraic. It looks scary, but it's pretty straightforward stuff. All right, so polyurethane microstructure, we've kind of seen this before. We have hard segments, soft segments. The hard stuff is the isocyanate, the soft stuff is the polyethylene. Room temperature, TG, is below room temperature. It gives you the amorphous rotary phases. Diisocyanate and the chain extenders that are used to make these high molecular weight can give you room temperature, or TGs that are above room temperature, and so you mix those two together into one polymer, and you get something that is halfway in between those two extremes. You can vary the amount of hard and soft segment and change the glass transition of whatever it is you're making. And then we have ring opening polymerization. And this is another way of putting things together that is a little cleaner. This is, think of this more like the polyethylene case, where it's almost it's a nice clean process where you don't see side products. You can ring open polymerize things, and so this involves taking a structure that consists of A and B, which is where the bond is going to break, and then you have whatever's connecting them, and whatever's connecting them is something useful. All right. So what happens is you heat this up or you expose it to a catalyst, the bond between A and B breaks, and they go out and they find other A and B bonds that are also broken, and they form a polymer, relatively large molecular weight polymer. The nice thing is there's no byproducts here. They doesn't react. And so why is this important? It's used to make something called polyglycolides, and this involves ring opening polymerization of this glycolide, not glycolide. And we make PGA. PGA is one of the first biodegradable synthetic polymers for biomedical use, and it's important because it replaces what used to be used, which was catgut. Anybody know what catgut is? It was not made with cats. No cats were harmed in the formation of catgut. Yes?
It's like a rough, cotton thread.
It's a cottony thread at the end, yeah, when you're done with it. All right, so back in the bad old days, when you went to the hospital and it didn't really matter what the wound was, but it's especially important if you have like stomach surgery. There's multiple sutures when you are sealing up the patient after stomach surgery, because they have the interior stomach and then the exterior skin. And with catgut, you had to go back and first off you had to get the stitches removed. All right, you guys probably aren't familiar with that phrase anymore, but it was something we all hated because they had to cut it and pull it out of your skin because it wasn't going anywhere, the catgut. And if you had stomach surgery, they had to open you back up again and pull it out of the wall of your stomach. All right. So surgery is only for surgeons. It's not for normal people. They make it sound simple, but never get surgery if you can avoid it. There's always things that can go wrong. PGA solved that problem because you can make a suture that would be absorbed by the skin or by the interior of the body. So both surgeries became irrelevant, all right, and surgeons lost work, which isn't a bad thing. PGA by itself is highly crystalline, 45 to 55% crystallinity. Melting point is relatively high. Glass transition is 35 to 40 C, which is perfect because it's right around body temperature. All right, so you look at that, maintaining that balance of good strength and some flexibility. So PGA is perfect for that. Low solubility, difficult to process, using solvent-related methods. However, it can be processed by extrusion, injection, and compression molding. So just like any other plastic, this fancy stuff can be run through an extruder and used to make objects, just like polyethylene is run through an extruder and used to make objects. All right, so it may be a fancy high-tech biomedical polymer, but it's still just a polymer. Works the same way. Great for fibers, good mechanical property. Polylactide came on board. It's a very similar material. Again, ring opening polymerization to give you this particular polymer called polylactide. Also useful in making different types of sutures. Has also been used to make things like bone screws as well. And so these are all examples of ring opening polymerization. And the next thing, or last thing I want to talk about is cross-linking to give us these thermoset type polymers. And again, it's all about the algebra, and it's all about some of the same functional groups we've already talked about. In this case, though, one of the monomers has more than 2 reactive groups. So we've been talking about linear polymerization to make long chains. Starts out with 2 and just grows and grows and grows in opposite directions. But if we have more than 1 reactive group on each end of the chain or somewhere else in the chain, then we can get growth in a different direction. And so we've been talking about this all along, but if I start out with a monomer that's got 3 active groups on it, 3 blue circles, then that can grow out in 3 different directions. Okay, and we add more, and we get greater and greater complexity in terms of branching. And so this is, when we think about cross-linking, you should be thinking about this. This is the type of reactivity we can have. And this is an example showing you the cross-linking itself. And so what we've got, again, maybe it looks a little scary, but it shouldn't be. We've got something in the middle, all right? And this is 8 CH2s in the middle there, a couple of carbonyls, all right? But we have our dear old friend hydroxy groups on the end, all right? So it's all the same thing. We don't care what's in between them. We know what's going to happen here. What we have over here on the left-hand side is what makes this a thermoset type structure. We have not just 1 or 2, but now we have 3 OHs on this other compound. So what are we going to make when we react these 2 together? Water, just like before, all right? No surprise. But in this context, we end up making something that's kind of hard to draw a thermoset in 2 dimensions. You've got a linear polymer chain, and then you've got another chain growing out in a direction away from that. And so what you see in this context doesn't look like much, but if we look at the mechanical properties, we have regular vulcanized rubber here. We have what's called polyisobutylene there, which is similar to the structures that are shown. They're both very rubbery, but that structure I just showed you, this P4HB, is very high modulus. All right, same groups that we used for polyisobutylene, but now because we cross-linked it, it doesn't move. It's a thermoset. And so we get these enormous elastic moduli for the system. It can be very brittle, but as I mentioned a minute ago, this can be used as an engineering polymer because obviously it can bear a load. Just don't drop it on the floor, but it'll bear a load pretty well. Okay. Any questions about that? All right. So the rest of this is a summary, which is why I was pushing things so I knew I could. So we're talking about step growth polymerization. Be familiar with the what C double bond O is, where it is in the structure, and what amides are, and so forth. And these are just, again, some of the classes of the polymers that we're making: polyesters, polyamides, polyurethanes. Be able to recognize these. Oh, by the way, so this is just showing you MA, monomer A, monomer B. That's what that means. Again, think of it, this is all part of what I've been saying. It's all algebraic. You can make monomer B whatever the heck you want to, and you know what the chemistry is at the end of the chains, regardless of what scary thing is in the middle of those monomer chains. Okay. And again, the Carruthers relationships, be familiar with X-Ben, P, and etc. Hopefully this issue, these needs for step growth polymerization are very familiar to you. And then these microstructural issues, how we're designing those, how we're engineering the amount of hard and soft segments in polyurethane, and what happens is, what we've always talked about all along, hydrogen bonding versus not. Polyethylene is not hydrogen bonding. The hard segments are hydrogen bonding. And then ring opening polymerization, which is really as simple as it sounds, but we do have some examples, some very scary looking things. All right, it looks kind of exotic, but in reality, if you go to your doctor's office, and they're a plastic surgeon especially, they'll have a cabinet full of different colored sutures, purple, green, yellow bags. All these are those sutures. These polymers are used in those sutures. So this is not an exotic thing. This is a very common thing in the area of surgery and suturing. And then, of course, when we talk about thermosets, not abstractly now, more concretely, we know what type of monomers can be used to make a thermoset. All right, any questions about all that? All right, again, so office hours are tomorrow from 3 to 5, online. I'll send out the Zoom invite. I guess we can just use the one I've already sent out, right? I'll send it out again. Okay, talk to you guys on Tuesday or maybe Wednesday, depending.